Hello, good morning, everybody. Okay, welcome to the next section, or to be exact, the last section of pressure, the pressure in gas, or gas pressure. Okay, in this section here, we look at the last segment of pressure, particularly pressure in gas, or sometimes we call this atmospheric pressure. Okay, the air that is above us. The concept is still the same as liquid. When we look at pressure, we look at what is above us. So let's say in the example previously, we look at the diving example whereby you're underwater. So what is above you is the level amount of water above you, but it's not just that. Above the water, you still have a lot of air. What we the air molecules, the air particles above us. So if you look at the pressure exerted onto the diver, other than the water level that's above them, you must also look at the air that's above the water. So it's like everything come crushing down on you. Okay, like what we have, you see like in this picture here, everything is coming down, crushing on you. Okay, so in this section here, we'll look at the pressure in atmospheric pressure. Now, pressure, like I mentioned to you, is looking at the amount of air forces exerted by the air. Okay, and we have a name for it. We call it atmospheric pressure. Okay, primarily, if you look at just air molecules, same thing is because of the air, the gravitational pull of the air molecules towards the center of the Earth. Okay, and you'll find that that layer of air, when it's being pulled by the gravity pull, it actually weigh down on us. And when it weigh down on us, particles, molecules being in random motion, they will actually exert a force onto us. Okay, and when they exert a force onto us, that force over the per unit area, or that pressure that we sense, is actually what we call atmospheric pressure. Okay, there's a number to it. Okay, you don't remember, it's around 100 kilopascal. Okay, or 1 with 50 at the back. Okay, now this number is what we call the atmosphere. Okay, 1 atmosphere, or 1 ATM. Now, if you look at it, that the amount of air weighing down on us is atmospheric pressure. So this is what we have at sea level. Okay, sea level, same thing. Whatever is below the sea, okay, the amount of water increases. Okay, your pressure by the water actually increases. But not just that. Okay, you have what is above the sea. You have all the air particle there here. Okay, that's exerting the pressure onto us. Okay, now, so like I mentioned before, at sea level, okay, let's say if you are here at sea level, okay, the amount of water, the amount of air above you is actually weighing down on you, and there's the atmospheric pressure. And if you go higher up, okay, if you are able to go up in the mountain, okay, you at higher up, you'll find that actually the pressure decreases. Okay, why? Primarily, same thing. The idea of pressure comes from stuff above you. So as the higher you go, okay, the amount of air that's above you, the amount of air that's available above you actually get lesser and lesser. And because the amount of air is lesser and lesser, the pressure or the force exerted on you per unit area will actually be lesser. Okay, that's why for Mount Everest, all these things, you will have like 8,000 meters above sea level, all these things, you'll find that the pressure is actually much, much smaller than what you experience at sea level. Of course, less pressure, more pressure. Yeah, definitely. It's like you need to get used to it. Okay, as long as you're not adapted to it, okay, you will fall sick. Okay, so that's one of the bad thing about high pressure and low pressure. Now, application of pressure, this particular section here, there's too much application to go through. Okay, so at this time, I'll leave it to your teachers, your respective teachers, to look at, to introduce to you the different type of applications that we see in real life. Okay, for example, most common one will be your suction cup and the syringe. Okay, even like simplest thing like drinking, sucking water from straws. It actually is a simple application of pressure. And most of these application that we are looking at, they actually have the same common keywords, or look at the working mechanism. Is actually we make use of pressure difference. Okay, whatever action that we do, for example, for the suction cup, when we press it, or even straws, when we suck up the air or suck up the water, any action or every action that we do for the applications, we actually want to do one thing. We want to achieve a single objective. Actually, we want to create a pressure difference. Because we know that when there is a pressure difference, okay, the force will act on it, and the force will always act in the direction that is from high pressure to low pressure. And because of that, okay, that force that's generated due to the pressure difference, actions or applications is able to be achieved. Okay, for example, a suction cup, if I can create a partial or what we call a low pressure region versus the atmospheric pressure, which is a high pressure, you'll find that there is a difference in pressure level, the high and the low. You'll find that the force will be exerted in the direction of high pressure to low pressure. And because of this force generated due to the pressure difference, my suction cap is able to stay on the wall for a very long time and able to carry weights that's hung on it. Okay, so this is what we mean by applications. Okay, this one I will leave it to your teachers. Okay, but do remember, most of the application that you see actually uses these two particular mechanism, whereby a force, pressure and force, differences in pressure generate a force. Okay. Now, the next section we look at is the measurements of pressure. We first thought we look at is atmospheric pressure. How do we know that the pressure is like 100,000 Pascal? How do we know one atmosphere is how big? Actually, we have a device, okay, which is barometer. Okay, the exact working mechanism, the user of mechanism, okay, I listed here. Okay, usually it's in most of the textbooks. Okay, I'll leave it to you to read it up. Okay, I'm more interested in like rather than making on a barometer, I'm more interested in like how to use it. Okay, now for barometer, this is what happened. Hey, where's the picture? Yeah, okay. Now, in the ideal barometer, you'll find that the spacing here is the tube is empty. This is what we call a vacuum. So what we have here is as the atmospheric pressure. The outside here is air. All these are air. The outside. Okay. All these are. And what's so fantastic about air is that you have a lot of air above that particular mercury. And this amount of air, the amount of air above the base of the exposed area of the mercury is what we call, it will exert what we call a atmospheric pressure. Okay, so this is the atmospheric pressure that is experienced by the mercury. So which means we are safe to say that at point A, okay, these two are the same, point B. Okay, point A and point B, they are experiencing what we call the atmospheric pressure, the air above it. But if I want to calculate atmospheric pressure, let's say example, point B. If I want to calculate atmospheric pressure using air, I will need to know the exact level, amount, or the height of the air above it. I will need to know the density of air and the planet that we are in. The main concern that we are in is how do we know how much air is above us if it's a very, very long distance. So it's like almost impossible to measure. It's like impragmatic. So what we generally use is we make use of the formula. We make use of relationship that pressure at A, pressure at B, so A and B are actually the same. And in fact, they're actually the same as C. So what we have is pressure at A is actually equal to pressure at B, and it's actually equal to pressure at C. One of the main reasons, like we mentioned in the last section, is pressure in the liquid. Why they are all the same? Because pressure A, B, C, they are in the same height level, which is here. They are same height level. They are in the same liquid, which is mercury, and they are in the same planet. So they actually have the same pressure. And the beauty about this is I actually can calculate, although I cannot calculate A and B, pressure A and pressure B, because I don't know the height of the air. But I actually can calculate pressure at C. Because pressure at C, I need height of C. Height of C is from here all the way up here. Okay, so this is what we call height of the, let me use another color. Okay, so I want to know, so I know the height of mercury above C. Okay, and I know that it is mercury, which I know the density of the mercury, which I can Google it. Is usually on the one of the constant that is available, and I know the planet G. So all I need to do is I just need to measure the height of the barometer, which it can be done, okay, because it's just less than 1 meter, okay, a tube, okay, and I know the density of mercury, and I know the gravitational field strength of Earth. So if I know Hc, rho, Hg, and G, all these three factors, I'm able to calculate the number here. And once I'm able to calculate this number, I will actually be able to derive the pressure at C and And similarly, I can actually get the PB and PA, pressure A and B respectively, because they are at the same point, same height, same liquid. And indirectly, I am able to calculate the atmospheric pressure. Okay, so essentially the mathematics here that I'm presenting here, okay, is riding on this, whereby pressure at A, B, C is actually the same, and because they are the same height, same level, same liquid, I'm able to calculate the atmospheric pressure, which is at B. Okay, this is atmospheric pressure, PATM. Okay, PATM. Okay, so this is how we generally use barometer. Okay. Now, if you look at the math, you'll find that the barometer, if you look at calculation, is actually 76 cm of mercury. Okay, it's equivalent to actually 1 atmospheric pressure. Okay, so sometimes we have a lazy way of writing it. So instead of calculating the Pascal or this thing, we actually like to write 760 Hg, mmHg. Okay, this number actually represents a few things. Okay, so we like to express it. Let's say the pressure, atmospheric pressure. We like to express it instead of like in Pascal, we like to express it 760 mmHg. Okay, this is more convenient. It's like easier because we don't need to actually press a calculator to calculate density of mercury. I don't need to deal with like a big chunk of numbers. So engineering wise, or people using a barometer, we like to leave it in this format because like, it's convenient. Okay, but this way of representation does give us the same information, meaning 760 mmHg means what? Means the height of the mercury that's available is actually 760 mm, or what we call 0.760 meter. And this information, 760 mmHg, it tells us another information. Because of the use of Hg, I actually know the density, the liquid that we use is actually mercury. And I know the density of mercury, 1360 kg per meter cube. So if I know these two information, okay, I actually know the planet Earth, which is 10 Newton per kg. I'm also able to calculate pressure ATM in terms of Pascal. But of course, I will do that when maybe I return back to office, when I have my calculator conveniently beside me, all these things, and when I'm not in the rush. So let's say in the workspace, okay, if you look at barometer, you want your answer fast. Instead of calculating, whipping out a calculator to calculate, we actually like to express it in mmHg. Okay, it's like more convenience. But 760 mmHg, it does allow us to convert to Pascal because of the information he represents. Okay, so students wise, you need to know how to convert like from mmHg to actually Pascal, okay, easily. Okay, so you must know what are the number they represent. Okay, so just to take note of this. Okay, now similarly, to go on to the diving questions that we have. Now, let's say if you are diving at 5 meters, okay, so let's say this is the 5 meters of water. So you are diving here. Okay, so this is 5 meters of water. There's above you, 5 meters. Okay, now at this point here, we are not just concerned about the water level above you. It's just that at this point, we are also interested in the atmospheric pressure, because there's not just water above you, not just this 5 meters of water above you. There's actually air above you also. So if you look at the pressure at this point, okay, the pressure at 5 meters where the diver is now, P5. The pressure at 5 meters P5 is actually not just by the water level. It's a water level plus the amount of air above it. So if you look at the wording, the pressure experienced by the diver at P5, 5 meters, is actually causing the water. Oh, wait, give me a minute. Let me use another symbol. Okay, so the pressure experienced by the diver is actually pressure of the water at 5 meters plus the amount of air above it, what we call atmospheric pressure. Okay, so these two combined will actually give you the total pressure experienced by the diver. And true enough, okay, this is what I written. Oh, it overlaps. Okay, so this is what I written here. So this is what we call your P5, and give me a minute. Okay, so this will be the pressure experienced by the diver. This will be P of atmospheric plus pressure of the water, P5. Okay, and we go back to the formula. Okay, Okay, so take a look at this. Okay, so this is P5, H2O of water. Remember, this is seawater. So if you look at the height you are interested in is the height in the water, plus, remember, density of water. At this point, we are not using air. H2O is the amount of seawater above it. So the density has to be seawater plus the planet. Okay, so if you press your calculator, you get the answer straight away. Okay, so in the nutshell, we're looking at, if we look at the pressure in air or pressure at the level, is actually what is above it. In this case here, we are just not looking at one layer of water. We are looking at everything that's above it, including water and the air above it. Okay. Similarly, is if your idea of barometer is not ideal, the barometer that you use is not ideal. So instead of vacuum, by right, this should be vacuum. Okay, so if it's not vacuum, means let's say it's not ideal. So I have air introducing. It could be like a mistake, a flaw in the production of a barometer. So in this case here, I will actually have air inside, and because I have air inside, I will actually have pressure inside it. So for example, if I want to calculate C, okay, previous example, why am I interested in C is because this pressure is actually the same. And PA, PC, I'm interested in PC. Why? Because PC is actually PA. Same level, same H, same rho, same G, same height, same water level height, same height, same liquid, plus same planet. So they are the same. And why am I interested in PA? Because PA, above PA is actually air. So I effectively saying PA actually is what we call atmospheric pressure. So in a nutshell, I actually can say that PC, PA, and P atmospheric, they are actually the same, even though they are on different part of the barometer. Okay, they actually have experienced the same amount of pressure. So why am I interested in PC? Same thing. PC allows you to calculate PC, means I need the stuff that's above PC, which is the mercury. And in this case, other than the mercury, I need the air. Okay, I'm also interested in the air. Okay, so there's an air section inside. So the left-hand side component, the two components will actually contribute to the pressure experienced at point C, which indirectly give us the pressure at atmospheric pressure. Okay. So same thing, if you are clear about the working here, you should be able to answer these two questions actually quite easily. Okay, same thing like I mentioned, how do I calculate the pressure? Okay, because the pressure at the top is no longer zero. Okay, the height of the mercury will fall. Yes, definitely, because why? PC is equal to P of the mercury plus P of the space. Okay, the airspace. Okay, so in the previously what we have done is we have an ideal barometer. Barometer ideal one, this section here is P vacuum. Vacuum means there is no pressure here. Okay, and there's no pressure. Okay, so now if I have a pressure here, if I have some pressure here, this number definitely will be less than 760. Okay, and so this is what the math we look at. Okay, now the mathematics, I'll leave it to you to work it out. Okay, so if you look at barometer in terms of the operations, okay, it allows us to find the mercury quite easily. It allows us to find the pressure of the atmosphere quite easily using the height differences in mercury. And similarly, we can also use other examples, other type of liquid. So instead of using mercury, I actually can look at water. But it's just sometimes we don't use water because water tend to be like the density is different, and actually the representation of the water barometer is actually quite different. Okay, why? Because you do a math correctly, you'll find that the water level, if I use a barometer, you fill with water. My barometer water barometer can actually be very, very, very tall. Okay, go back. Okay, homework for you if you want. Okay, you can actually work out. If I don't use a mercury barometer, if I use a water barometer, for the same atmospheric pressure, how high is my water level? And you'll be surprised, it's not 76 cm. Okay, now take a look. Okay, now the next section that we look at is another device to measure the difference in pressure, which is your manometer. Okay, now at this section here, before we start, okay, this section here, remember this is another device already. But if we still look at measuring pressure, okay, using differences. Okay, now what we have here is this is what we call a J tube or U tube lah. Okay, so whereby you have two opening here. Okay, these two opening, it can be one of the opening can be stuck in maybe a container or maybe a opening and you want to measure the pressure in the opening, and by doing some mathematics we will go through later, you'll be able to calculate the pressure in that particular container. Okay, just by the difference in the mercury. Now, so let's say now I have one opening here into the gas. So I'm supposed to find PB. So PB is what we call the pressure of the gas. So I want to calculate the gas. Now, normally what we do is we identify the high end and we identify the low end. Okay. So normally for manometer, okay, you identify the high end and you identify the low end. Okay, so this is the high end, this is the low end. And the math that we are looking at is quite simple. Okay, just need to take note of it every time you do this. For manometer, okay, always look for the low end. Okay, why do I want to do that? Because at the low end, okay, PB, I will able to be equate it to PC. Okay, I will be able to see such that PB is actually equal to PC. Okay, why are they equal? It's because they are the same level, same mercury, and the same height level. Same height level, same type of liquid, same planets. So the two of them, B and C, will actually be the same pressure. But conveniently is what we want is the next step. Okay, the important one is the next step. Because they are the same, I can actually represent PB in terms of PC and what is above C, which is a level of mercury plus a level of air all the way up in the air. So PC, I can effectively say is by the amount of mercury that is above it plus the air above it, which is PO. Okay, so if you look at it, you now have a mathematical representation of PB, PC, and atmospheric pressure. And the beauty about piece B and C, why do I want B? Like I mentioned to you, B is actually what we call P gas. I want to measure the pressure at gas. Okay, so now I have a formula to relate gas to the mercury level and the atmospheric pressure. So once I have this equation out, I can actually apply my math and substitute any values that I want to calculate any sides of the equation. And usually, most of the case, I actually want to calculate the pressure of gas. Because pressure of gas is the unknown. I want to know what is the number there. PO, I can actually look up Google or Wikipedia or even like some scientific journals to calculate the atmospheric pressure. H rho G, H, I can actually just look at my manometer, this device, to see the height itself, so there's no ambiguity. So left-hand side, right-hand side, these two items I actually know, so I can actually work them out and to calculate the pressure in the gas itself. Okay. Now, so another example that we look at is this. Okay, so same thing, what we are looking at, okay, manometer, okay, with different levels, with different liquid in fact. So what you do is, first thing you narrow down is you look at the lowest region. You look at the low end, the one with the lower tip. Okay, you look at PA. Okay, now what happened is I want to equate them together. And you'll find that PA and PB, okay, PB, what is PB? PB consists of a level of water here. Okay, so a level of water, a level of mercury, okay, which is controlled by H15 rho of mercury. Sorry, it's not mercury, it's alcohol, sorry. And G of the planets. Okay, so this is what is on the right side. PA on the other side, same thing, it's the same concept of pressure of liquid, is anything that's above it. But it's just that instead of alcohol now, I have actually a layer of water, which is H12, rho of water, and the planet Earth. Even though the whatever is above them at A and B, they are different. One is alcohol, one is water, but the concept is the same. The pressure that's above them is actually what is causing the pressure at B and A, sorry. Okay, and because A and B are at the same level, same height, the number is actually the same. In this equation, we have left out something else. Okay, for PB, other than the alcohol, we actually have a layer of air, which is what we call atmospheric pressure. So PB, you should have something called atmospheric pressure. Similarly, on A side, above the water, don't forget, you still have a layer of water, air, so you actually have a PO here. Okay, so remember, pressure is anything and everything above you. So you must include the air also. Okay, but of course, if you look at the math, you'll find that PO on the right side and PO on the left side, they will actually cancel out each other. The difference between them will give you 0 straight away. So if you look at the math, sometimes we just conveniently leave out PO. But in concept wise, okay, it's actually good to know that the PO is always included so that we will not, it's just that sometimes you look at math, they may not cancel out, but you need to know that it is there. Okay, then after that, you look at the math, you can submit the value. You have height of the water, height of the alcohol, you have the density of the water. Okay, so you have this item to you given, H12, H15 is given to you, G is given to you, 10 Newton per kg. So water is given to you, and all you left in this equation is to calculate the density of alcohol, which can be found, okay, using a simple algebra equations. Okay, you can work on it and you find that the answer will be actually 800 kg per meter cube, okay, for this particular section. Okay, and similarly, okay, I have another example here. Okay, you can take a look at it. Okay, I will not go through too much. Okay, because the idea is actually the same. Okay, so if you look at barometer, the main things that we are looking for, example here, this will be PA, this will be PB. Always look for a barometer. The first thing is always look for the lower end, because I want to have an equation that join both tube or both limbs together. So PA, okay, is actually equal to PB. The only difference now is, okay, PB is actually a level of mercury and the gas. So I will have H rho G plus the gas. And similarly, PA, okay, what is above PA is atmospheric pressure. So this is what I call PO. So once I have the equations that join the both limbs together, I'm all good to go already. I can just use my math and I can just find whatever I need it ASAP. So remember, in our treatment for manometer, remember the thing about manometer is the idea of using it. You must be able to know how to use manometer, and that's where the physics will come in. So the idea of the physics is to identify which section is the same, which section have the same pressure. And why you want to do it is because I want to have an equation to generate equations that links the two pressure points together, or what you call the two tubes or two limbs together. Yeah, and when I do that, once the equation is formed, I will let the math take over. I will let the algebra take over to calculate anything that is of interest to me. Okay, and this is where we end off for manometer and barometer. So barometer, okay, there's two things that we look at, and manometer. Okay, the treatment for it is slightly different between each other, but the main concept we drive at is same thing. Anything pressure at that point, it comes from anything and everything above it. Okay, so once you take note of this particular concept or this particular rule that we're looking at, you can actually apply it to your barometer and your manometer, and that's where the math will take over. So you need to get yourself familiarized with the math also. Okay, so if not, okay, this is where I end here for this particular section. Okay, if you have any questions for barometer and manometer and barometer, okay, feel free to leave me a comment or even drop me an email. Okay, okay, so that we can run through any sections that you are confused or you need me to actually go through in depth. Okay, if you need to, okay, we can meet up face to face. Okay, for my students. If not, actually, I can generate a new. I can actually record a video that actually that has what you want, so that we can together, we can learn together. Okay, not just you clearing your doubts. Okay, other students, other viewers can actually learn more in detail. Okay, with that, see you